What is going on, guys? This is John Nahas from Period One of Chemistry Honors, here to explain how to make a Lewis dot structure. So let's start off by assessing what compound we're going to be working with. So here we see we have disilicon, difluoride, and dihydride. That's really what we're going to be working with. So the first thing that I like to do before actually writing out the dot structure, and really a prerequisite to doing the whole process, is to count for the total number of valence electrons that we're going to be working with. So the way to do that's pretty simple. What you do is you locate each respective element on the periodic table and see how many valence electrons one of those atoms actually has. So if we go to silicon, for example, we see one atom of silicon has a total of 4 valence electrons. So since we're working with 2 silicons, that's going to yield a total of 8 valence electrons that we're going to be working with. Remember that E with the dash next to it is the notation symbol for valence electrons. So next when we move to fluorine, we're going to see that one fluorine has 7 valence electrons, so because of the 2, remember, it's going to be 14. And doing the same thing for hydrogen, we get 2 valence electrons. This ultimately leads to a grand total of 24 valence electrons. That's how many we're going to be working with. The next thing that I like to do is do the Lewis dot structure per each respective element. So silicon, for instance, we know that one silicon atom has 4 valence electrons. So the way you would do that is you'd write Si for silicon, and then you'd fill each orbital in descending order, starting with filling out the first orbital. So 1, 2, 3, 4. So now that we have the Lewis dot structure of silicon, we could move on and do fluorine next. So fluorine, using the same rule, will have 1, 2 dots in the first orbital, 1 dot, 2 dot, 3 dot, and then you just fill it in descending order, and that would yield a total of 7 dots, i.e. 7 valence electrons. Remember that silicon's kind of a special case because it doesn't have 2 valence electrons in the first orbital. So lastly with hydrogen, we remember that hydrogen has 1 valence electron, so that's just going to be 1 dot in the first orbital. So the next thing that we have to do is find the total number of bonds that we're going to be working with. So the way we do this is we find the total number of valence electrons, we divide that by 2, so in this case it would be 12, because 24 divided by 2. That's the total number of pairs that we're going to be working with. So the next thing that you want to do after you calculate the total number of pairs is subtract the total number of, quote, unshared pairs. The way to do this is we look at our dot structures, we see, okay, so we have 3 unshared pairs, 1, 2, 3, and then we look to the fact that we have 2 fluorine atoms, so that's going to be a total of 6 unshared pairs. So by subtracting 6, we get a grand total of 6 bonds. So the bonds is going to be really a great way to check our work, and it'll really come into play later. So now when we're actually making the structure, what you want to do is you want to locate the element with the lowest electronegativity and the most open spaces, and in this case it's going to be silicon. So we put silicon in the middle. So you want to just copy down the dot structure, so we're going to see 1, 2, 3, 4, silicon again, 1, 2, 3, 4. So you could see 2 valence electrons are touching, that forms a single bond, so you could connect that and represent that with a line. So now we could really cross silicon off. Next, let's work with hydrogen because it's only 1 valence electron, and it'll be really easy to pair with the 1 valence electron of silicon. So we do the 2 hydrogens, so that forms a single bond. Same thing here, forms a single bond. So now that we're done with the hydrogens and the silicons, we just have to worry about the fluorines, which luckily is pretty easy. We can see that it's 3 of the orbitals are full and have 2 valence electrons. So it's going to be really easy to share with the one orbital that isn't full. So we could just do fluorine representative like that. Make the bond. Do the same thing on the other side. Let me just... One, 2, 3, 4, 5, 6. So really quickly, what you want to check for is whether each element's fulfilling whatever rules it has. So hydrogen states that it'll have 2 valence electrons, so it's fulfilling the rule of duet. And fluorine is fulfilling the rule of octet because it has 8 valence electrons. So lastly, you want to check, do you have the total number of bonds? The answer to this is no. We only have 5 bonds currently, but that's simply because of the fact that we have 2 solitary valence electrons in the first orbital not being occupied. So the simple solution to this is you shift these electrons down to the center. And silicon actually forms a double bond. So now when we check, we have 1, 2, 3, 4, 5, 6 bonds. 6 bonds as we did in our math earlier. We see silicon and fluorines fulfilling the rule of octet, hydrogen the rule of duet, and this is ultimately how to make a Lewis dot structure. Alright guys, I'm back for the second part of this video, and we're going to be analyzing the last compound that we're going to be finding the Lewis dot structure of. So I'll be going through the steps a little bit quickly, simply because of the fact that we've went over them in the last part of the video. So, we find the total number of valence electrons. So that's 7 for manganese. For oxygen, that's 6. You multiply it by 4, that's a total of 24. Realize that the -1, which is the only delineation between this set of atoms in the last set, is the -1. So what that -1 charge yields is an extra electron, so it's actually going to be 24 plus 1, so that's 25. That yields a total of, if we add these up, a grand total of 32 valence electrons that we're working with. Next, what I like to do, as you know, is do the Lewis dot structure per respective element. So for manganese, that's going to be M, and since it's 7, 1, 2, 3, 4, 5, 6, 7. So we're filling the orbitals in descending order. That's a total of 7 valence electrons filling the orbit as consistent in the periodic table. With oxygen, it's a total of 6. So 1, 2, 3, 4, 5, and then you just go in descending order, so 6. So we have the baseline structures that we're working with. Next, what we have to do is find the total number of bonds that we're going to be working with. So that's simple. What you do is you divide the total number of electrons, as shown in the last part of the video, by 2. So that's going to be a total of 16 pairs. 16 pairs. So next we're going to want to subtract the total number of unshared pairs. So for this, we're actually going to have to do a little bit of work to find the unshared pairs. So I just put parentheses so we could actually show our work. So we see for manganese, since there's only one of them, it's going to yield 3 unshared pairs. Now with oxygen, this is the interesting one. We see 1, 2 unshared pairs initially. Multiply that by 4. That's a total of 8 unshared pairs. But remember the -1 charge that yields an electron. If you actually apply that towards oxygen, that actually accounts for an extra 1 valence electron to work with. So that's a total of 12 valence electrons that we're going to be subtracting, which is going to lead to 4 bonds that we're going to be working with. 4 bonds. So next, what we're going to have to decide is which element we want to be central for our Lewis dot structure. That's going to be manganese. So if we put manganese like that, and we actually fulfill and copy down the dot structure that we previously did, we'll have that. So this is pretty critical that it has 3 orbitals fulfilled. That means oxygen really doesn't have to share any of its electrons. So what you could do for the first 3 orbitals is shift one of the electrons of oxygen over, and that's actually going to yield oxygen represented like this with single bonds between them. So single bonds, I'll go ahead and fill it out. So it's going to be single bonds, and oxygen will be fulfilling the rule of octet because it has 8 valence electrons. 1, 2, 3, 4, 6, 7, 8. So the last part of the thing that we have to do for this total Lewis dot structure is pretty simple, but it involves a little bit of thinking. So we're going to have this -1 valence electron, this -1 charge, which yields a valence electron. That's going to come into play because for this one, manganese actually does in fact need a valence electron to make the bond. So we're going to use that. We're going to use the 1 solitary valence electron of oxygen to make a single bond. So we have oxygen making a single bond. I guess you could cross that. We have the 2 valence electrons in the outer shells fulfilled like that. And then currently, as it stands right now, there's only 1 valence electron in that last 4th shell. But that's where the -1 comes into play, is the last valence electron really fulfilling the shell, fulfilling the rule of octet. So ultimately, you're going to put that in brackets, put an old -1 next to it to represent the total negative charge, total number of extra valence electrons that were received. And that really concludes how to make a Lewis dot structure video. Thank you.